Good evening. Today, every school child knows that atoms are consisted of subatomic particles. But this, of course, is quite a recent concept resting on the shoulders of people like Madame Curie, her husband Pierre, and Rutherford. Up to that time, scientists and philosophers from almost the beginning of time, from a man called Democritus, which is 5th century BC, predicted that there were atoms, and these atoms would never change. Now, Madame Curie, although she was basically a physicist and a mathematician, was very familiar with chemistry. And certainly she was familiar with chemical explosions. For instance, gasoline. You put gasoline in your car, it combines with oxygen, you have an explosion, and on the right side of the equation, you have water, heat, and a lot of other stuff. That's a chemical explosion. The energy comes from the chemical bonds. But in the universe, most explosions are not chemical. They are atomic, a better word would be nuclear. In fact, the origin of the universe was actually what was called the Big Bang theory of the universe, first proposed by my father and his students back in 1948, and known as the Big Bang theory of the universe. Just about the time my father and his students were working, other astronomers, astrophysicists, made measurements in the heavens that actually, if you look back in time, you go back and back light years behind, you can see what the universe looked like 100 years ago, 1,000 years ago, 1,000,000 years ago, 1,000,000 years ago. You kind of have these photographs out there. And sure enough, the universe is expanding. You can now calculate what the temperature must have been at the universe at different ages, because you can look back like a time machine. You can look back in space. And he came up with a few degrees, I think it was 6 or 8 degrees above zero. Recent experiments by Penzias and Wilson, a Nobel Prize winning group, found it to be 4 degrees absolute. So father and his group are pretty close. So if you can now predict what the decrease in temperature as the universe is expanding, just like any gas that expands, like in your refrigerator, cools. If you do the opposite, if you contract it, and what we can now do, particularly recently with our computers, we can say, aha, let us run the tape, the film backward, and see what happens as we go back earlier, and the recent calculation will go back 13.7 billion years. And that's the birthday of the universe. Now, one of the big problems that we have in physics today, an unsolved problem, where did mass come from? We know how to measure mass of all these particles, whether they're quarks, neutrons, protons, electrons, but where did the mass first originally arrive? And it was really at the Big Bang. So could we human beings in our genius, simulate the conditions that occurred just at the time that the Big Bang occurred? We know it was hot. We know it was very dense. And using something we call Hadron Colliders, a group of scientists in the last, it's a little confusing, last 2 decades, certainly the last decade, tried to answer that question: what existed just at the time, or maybe a billionth of a second after the Big Bang, when everything was dense and hot? Why would they know that? Why would they want to know that? And it comes out of Einstein. Now, Einstein came out of an equation, E equals mc squared. It must be the most beloved equation in the world. But what does it really mean? What was the revolution in Einstein's point of view? And what he said, that energy means anything that could push and move a stone is energy, is exactly the same as mass. And they're interconvertible. The fact is that a little bit of mass, if you look at that equation, E equals mc squared, a little bit of mass produces a fantastic amount of energy. And that multiplication factor, like we have in currency, is the speed of light squared. And so what the scientists want to do, and they have now built a large Hadron Collider in Geneva, is to be able to simulate very closely the exact time, the exact conditions immediately after the Big Bang. And so to do this, they built a tube 17 miles long. And they sank that tube underground, 300 feet. And now comes the tricky part. You want to simulate absolute, maybe 1 or 2 degrees above zero. And you want to have it empty, nothing inside, as close to vacuum as you can have. And that condition is in that tube, 17 miles long. It is the coldest and emptiest spot in the solar system. There's no place in the solar system which has those conditions now. But 300 feet underground, they have those conditions. So now the trick is, let us take a beam of protons of the nucleus of a hydrogen, and by using many magnets, something like 10,000 magnets, you begin sucking these protons around this tube. So they start going faster and faster and faster. Every time it goes by one of these magnets, you kind of kick it, it goes a little faster. It's going so fast that it goes 11,000 times a second around these 17 miles. Well, what do we do that for? But once we get that group going, we'll shoot another beam of protons the opposite direction. And occasionally, they will collide. Now, these protons are going at, I had to count, 99.99999% the speed of light. Each one is going virtually within a minuscule speed of light, and they collide. Can you imagine the energy released? Well, according to Einstein's equation, E equals mc squared, if you have that much energy, you'll get a new mass. And what the scientists in the Large Hadron Collider want to look at, what do you get? Will you get asymmetrical particles? We don't know. Will you get micro black holes? Because a black hole could be any size. And you all know that a black hole is so dense, and the gravity is so strong that even a beam of light can't get out. So this is a very, very tricky experiment. And of course now, the soothsayers are saying, well, if they now make a black hole underground in Geneva, the black hole will swallow Switzerland, it'll swallow the United States, it'll swallow the Earth, and we'll all go into a black hole. Well, in truth, we know that that won't happen. But it'll be the most exciting thing would happen, certainly in science, I think, this century, is to be able to simulate what has happened right after the Big Bang.